Hello, I'm Dr. Samidhi Navaratna from the Department of Community Medicine. Well, this is the third lecture of the Inferential Statistics lecture series, and I'm thankful to those who took the trouble to fill up the feedback forms and submit the answers to the quizzes following the last two lectures. Through those, I was able to identify certain gaps and areas that need further clarifications. Therefore, I thought I would discuss some key points from the last two lectures before we move to the lecture proper, because I feel there's a bit of a need to discuss certain areas deeply. Before we start the lecture proper, let's try to recap what we have learned so far. If you can remember, in the last two lectures, we discussed about two inference procedures to draw conclusions about a population. When our goal is to determine the difference, we used confidence interval. When our goal is to test a claim about the difference, in other words, to test a hypothesis, we used a hypothesis test. Both these inference procedures are based on the sampling distribution. Then we learnt a common formula to calculate the confidence interval in the first lecture. Then in the second lecture, we covered z-test and t-test. Last week, we learned about using the z-test for hypothesis testing. We used this common formula to derive the respective formulae for the one sample z-test and two sample z-test. Because we do not know the population standard deviations, we estimate them using the sample standard deviation in one sample z-test, and from our two independent samples we get the standard deviations in our when we want to compare two sample means. Similarly, in the last lecture, we learnt about the t-test and we used the same common equation to derive the formulae. We learnt about three types of test: t-test, one sample t-test, two sample independent t-test, and the paired t-test. For the two sample independent t-test, we calculated a pooled standard deviation, which is a weighted average actually. So it's a method for estimating a single standard deviation to represent all independent samples or groups, so that we are assuming there that they come from a common population. So we think that they have a common standard deviation according to the null hypothesis. We learned about the critical values for important significance levels when using the z-test. So if you can remember, I told you that it would be good if you can by heart these critical values, particularly those corresponding to the 95% confidence level and 99% confidence level. Then we learnt about the confidence intervals. We learnt how to construct confidence intervals for one sample, and this is the common equation we used. So I'll just write down the 99%, I'll write the 90% confidence interval, and the 95% confidence interval, just to let you know how you can derive any confidence interval using this common equation. Then similarly, if you can figure this out, we can derive confidence intervals for the difference between two samples as well. And this is the common equation that we would be using. If we put down the 99% confidence interval, it would be like this. So instead of the sample statistic here, the mean, we just put the difference between the two samples here, the difference between the means. Then we put the standard error for the which we used for the difference between two samples. See. Adding a little bit to the constructing of confidence intervals, well, it would be interesting for you to know that you can actually use the t values in the place of z values. So when can this be done? So first question you need to ask is whether you know the population standard deviation. So if so, you can straight away use the z values irrespective of the sample size. But of course, if the sample size is less than 30, the population must be normally distributed. Then, secondly, if the answer is no, if you don't know the standard deviation, then you have to ask a second question, that is whether the sample size is greater than or equal to 30. If so, you can still use the z values, and in the place of population standard deviation, you can use the sample standard deviation. And if the sample size is less than 30, then you can use the t values, and in the place of the population standard deviation, you can again use the sample standard deviation in calculating the standard error. Let's reiterate the steps we followed in hypothesis testing. First one is state the null hypothesis and alternative hypothesis. Second one, find the critical values. Third one, compute the test statistic. Fourth one, compare the calculated value with the critical value and decide whether to reject null hypothesis or not. And then finally, we summarize the results. As in the constructing of the confidence intervals, it's important to know when to use the z-test and the t-test. So similarly, you need to first see whether you know the population standard deviation. If yes, you use the z-test irrespective of the sample size. Again, if the sample size is low, that is less than 30, the population must be normally distributed. Secondly, if you don't know the standard deviation of the population, you have to ask whether the sample size is greater or equal than 30. Then, if the answer is yes, then you can again use the z-test with standard deviation of the sample used instead of the population standard deviation. Then, if the sample is smaller than 30, then you can use the t-test with the standard deviation of the sample in place of the population standard deviation. Moving to the lecture proper, last time during the Inferential Statistics 2 lecture, you learned about hypothesis tests involving means and difference in means. Today's lecture is on proportions. Therefore, you will be learning about hypothesis tests involving proportions. By the end of this lecture, the student should be able to identify notations used for proportions. Then, calculate standard error of a proportion for one sample and for difference between two samples. Calculate confidence interval of a population proportion for one sample and for difference between two samples. Carry out hypothesis testing using one sample is a test for proportions. Then finally, carry out hypothesis testing using two sample is a test for proportions. In this lecture, we will learn two inference procedures to draw conclusions about a population proportion. First one is, we'll be using a confidence interval when our goal is to estimate the difference. And secondly, we will learn about hypothesis tests that can be used to test proportions when we want to, test a claim about a difference. Some points you need to remember when you are carrying out a hypothesis test involving proportions. Most of the time, people are not interested in making inferences about a population mean, but rather they are interested in inferences about a population proportion. Then, a hypothesis test involving a population proportion usually has two outcomes. Therefore, they are known as binomial distributions. Usually, the population proportion is denoted by pi and sometimes by capital P or simple p. Whereas the sample proportion is denoted by the symbol simple p. To avoid the confusion that sometimes it is denoting the population proportion, we use instead of simple p, we use the p hat as a symbol for sample proportion. The distribution of a sample variable approximates a normal distribution, that is a bell curve, as the sample size becomes larger, assuming that all samples are identical in size and regardless of the population's actual distribution shape. If repeated random samples of a given size are taken from a population where the proportion is the category of interest, then the mean of all sample proportions in that distribution is equal to the population proportion. And that distribution is called the sampling distribution of the proportion. Similar to constructing confidence intervals for means, we will try to learn to construct confidence intervals for estimation of a proportion and for estimating a difference between two proportions. As you already know, standard error is needed for calculation of confidence intervals. Let's see how standard error is calculated for proportions. This is the formula for calculation of standard error of a proportion for one sample. Since the population proportion is unknown As shown here in this formula, sample estimate is used. Some books use Q in the place of 1 minus P hat. This is the formula used to calculate the standard error between two proportions. Let's see how the confidence interval of a proportion is calculated. For one sample, the general equation is this. As you can see, it's not much different from the equation we use to calculate confidence interval for the mean. So, the 95% confidence interval for population proportion would be sample estimate plus or minus 1.96 into standard error of the sample estimate. And the 99% confidence interval would be this. And to calculate the standard error, we will be using the equation we just learned. Similarly, for the difference between two proportions, the general equation is given by this. And as you can see, it is also not different from what we learned for the difference between two population means. Therefore, the examples, 95% confidence interval for the difference between two population proportions is given by this formula, and for 99% confidence interval, this is the formula. And as you learned just now, the standard error for the difference between two proportions is given by this formula. So you need to substitute the result of this to this equation. Let's look at an example for calculation of confidence interval for proportions. Out of a sample of 200 antenatal clinic attendees, 20 were detected to have anemia. Estimate the proportion of anemia among the antenatal clinic attendees in the population. Second part is estimate the 95% confidence interval and the 99% confidence interval for the above calculated estimation. The first part is quite simple. You just need to calculate the proportion. And it's 20 out of 200, and that comes to 0.1. When given as a percentage, it's 10%. And to calculate the 95% confidence interval and the 99% confidence interval, you need to calculate the standard error first. So this is the equation. You just need to substitute the calculated sample statistic into this equation. The answer is 0.021. So using this estimate for the standard error, let's calculate the 95% confidence interval. This is the equation. And the answer is 0.059 to 0.141. When given as a percentage, it would be 5.9% to 14.1. So if we interpret this, This means that we are 95% confident that the population mean for the anemia among the antenatal clinic attendees lies between 5.9% and 14.1%. So, in a similar fashion, we can calculate the 99% confidence interval. So the answer is 0.046 to 0.154. When given as a percentage, it's 4.6% to 15.4%. So again, we can interpret this as that with 99% confidence, we can state that the proportion of anemia, that is the population proportion of anemia among the antenatal clinic attendees lies between 4.6% and 15.4%. So, if you don't like working with decimals, you can use this equation for calculation of standard error. Now, take a look at these confidence intervals. When you look at the 95% confidence interval, you can see that it is narrower than the 99% confidence interval. So, when the level of confidence increases, the range of values widens. When the confidence level increases, the confidence interval widens. Narrower confidence interval implies higher precision and vice versa. So that is one point you should note. Let's look at another example for calculation of confidence interval for proportions. In the first round of vaccination of the elderly against SARS-CoV-2 with the Sputnik vaccine in Kandy district, 594 out of 667 eligible individuals were vaccinated in the Mavilmada Grama Niladhari division, while 286 out of 362 were successfully vaccinated in the Senkadagala Grama Niladhari division. Find out the 95% confidence interval for the difference in vaccination acceptance rate and interpret the results. So first we need to find the vaccine acceptance rate for each Grama Niladhari division. For the Mavilmada Grama Niladhari division, it's 89.05%, and for the Senkadagala Grama Niladhari division, it's 79%. So the difference is 10.05. So we'll use that to calculate the standard error for the difference between these proportions. So the answer is 2.45. Now the next step is to use this calculated estimate for the standard error for calculation of 95% confidence interval. So you know the equation. So we'll just substitute these figures, these relevant figures to this equation and simplify it. So the answer is 5.24% to 14.86%. And how do we interpret these results? One way is that you can say with 95% confidence interval, that the difference between these true population proportions lies between 5.24 to 14.86. And most importantly, we can say, since the null value, that is no difference or no association, which is actually 0, it's not included within the confidence interval. The difference between the vaccination acceptance rates in these Raman-Niradhari divisions is statistically significant. So note, when the confidence interval contains a value that implies no change, no association, then the result becomes statistically non-significant. Now that we have finished learning about construction of confidence intervals for proportions, let's move to the hypothesis testing for proportions. Steps followed in hypothesis testing of proportions are the same as the steps followed in hypothesis testing of means. If you can remember, we have already discussed these steps at the beginning of this lecture. However, it definitely won't be a waste of time if we go through it again in the context of hypothesis testing of proportions. So let's see the first step. State the null hypothesis and alternative hypothesis. Second step, find the critical values. Third step, compute the test statistic. Fourth step, compare the calculated value with the critical value and decide whether to reject null hypothesis or not. And finally, summarize the results. Moving on to one sample z-test for proportions. This test is used to estimate the true population proportion. Certain assumptions are made in applying one sample z proportion test, and those are, the data are from random sampling from the population. The second one is population follows a binomial distribution. Third one is when sample size is large, this binomial distribution approximates a normal distribution. Formulae for the one sample z-test for proportions. This test also follows the same format. Test value equals observed value minus expected value divided by the standard error. We already know how to calculate the standard error for the proportion. The observed error, that is the observed value minus expected value, is written as p hat minus p divided by the standard error for the proportion. Now, as we discussed, if you don't like decimal points, dealing with decimal points, you can use the percentages, and you can use this equation instead. So the key to the equations is the test statistic. P hat observed proportion, P is the hypothesized probability, and N is the sample size. Let's look at an example for one sample z-test for proportions. It is claimed that 15% of COVID-19 positive patients develop severe pneumonia. A researcher who wants to test that claim observes 560 severe pneumonia cases among 4,012 confirmed cases of COVID-19 patients admitted to a hospital. That is 13.95%. Test the claim at alpha equals 0.05 level. So the first step is to state the null hypothesis and the alternative hypothesis. So, if you read this again carefully, what we are going to check is, we are going to see whether the population proportion is the same or different to 15%. So, the null hypothesis is P equals 15%. Alternative hypothesis is, that is what the researcher wants to prove, that is P is not equal to 15%. So, the next step is to find the critical values. And we know that because this is a test of no difference, it's a two-tailed test, and the corresponding critical values for the alpha equals 0.05 level is 1.96. Two-tailed and critical value 1.96. The third step is to compute the test statistic using the Z test for one sample proportion. The result is minus 1.86. Fourth step is to compare the calculated value with the critical value and decide whether to reject null hypothesis or not. So let's look at the diagram again. This calculated value minus 1.86 falls outside the critical region, right? It is towards the right of this minus 1.96. Therefore, we cannot reject the null hypothesis. So let's summarize the result. Since the calculated Z statistic falls outside the critical region, the null hypothesis cannot be rejected. Therefore, the claim that 15% of COVID-19 positive patients develop severe pneumonia can be accepted at 5% significance level. Moving on to the two-sample Z test for proportions. This test is used to determine whether two population proportions differ significantly on specific characteristics. Basically, categorical characteristics, variables. Okay, so the assumptions made are similar to that of one sample Z test for proportions. The data are random values. Both populations follow a binomial distribution. Samples are independent of each other, and test results are accurate when sample sizes are large. Formulae for two-sample Z test for proportions also follow the same common format. Test value equals observed value minus expected value divided by the standard error. We know already, we have learned how to calculate the standard error for the difference between two proportions, and this is the equation for the test statistic. And if you are more comfortable with using percentages than the decimals, you can use this equivalent counterpart of the equation. The only difference is that you use 100 here instead of 1. And just to remind you of this simple arithmetic of calculating the proportions, I have included this, how to calculate p hat 1 and p hat 2. And in particular, it's important to note that since the null hypothesis states that P1 equals P2, we use a pooled sample proportion to compute the standard error of the sampling distribution of proportions. So the pooled proportion is x1 plus x2 divided by n1 plus n2. In case you don't know how to derive x1, you can use these equations. And according to the null hypothesis, the P1 equals P2. So this part of the equation, becomes 0. So we are left with P hat 1 minus P hat 2 for the numerator, and standard error, the standard error for the denominator. Let's look at an example for hypothesis testing using two sample Z tests for proportions. In an exercise intervention study, 30 out of 50 participants in the test group had lower triglyceride levels following the intervention period compared to 20 out of 80 participants in the control group. Is there a significant difference between the two proportions at 0.05 significance level? So the first step is to state the null hypothesis and alternative hypothesis. So we are talking about a difference here. No difference. Null hypothesis should be no difference. And then we need to write the null hypothesis as P1 equals P2 or P1 minus P2 equals 0. And the alternative hypothesis as P1 does not equal P2. Find the critical values. So look at the significance level. It's 0.05. Therefore, it's a two-tailed test with the critical values 1.96 at each tail end. The third step is to compute the test statistic. For that, we are using the Z test for comparing two sample proportions. As the initial step, let's calculate P hat 1 and P hat 2. P hat 1 turned out to be 60%, while P hat 2 turned out to be 25%. Taking into consideration the null hypothesis that states P1 is equal to P2, that is, the true population proportion of the first sample is equal to the true population proportion of the second sample. So therefore, if they are equal, we have to come up with one estimate. Therefore, let's pool the proportions and come up with one sample estimate for the population parameter. That is 38.5%. Now, all we have to do is apply these test statistics, the estimates we came up with to this equation. One more thing is that according to the null hypothesis, we have stated that P1 is equal to P2. Therefore, P1 minus P2 will become 0. The calculated Z score is 3.99. The next step is to compare the calculated value with the critical value and decide whether to reject null hypothesis or not. Let's look at the null distribution again. And as you can see, the calculated Z score falls within the critical region. The calculated score is way beyond the critical value. Therefore, we can reject the null hypothesis. So let's come up with a summary. The calculated Z score is larger than the critical value. Hence, reject null hypothesis. The difference observed is statistically significant at alpha equals 0.05 significance level. What are the other tests that can be used for hypothesis testing of proportions? Apart from the Z test, there is chi-square test, Fisher's exact test, and goodness of fit test. The chi-square test and the Fisher's exact test use contingency tables to calculate the test statistic. So we'll be learning about chi-square test in the next lecture. So now we have come to the end of this lecture. In today's lecture, we learnt about construction of confidence intervals for proportions. We also learnt about hypothesis testing with one sample Z test for proportions. And we learnt about hypothesis testing with two sample Z test for difference between two proportions. So if you have any doubts, go through this lecture a couple of times, and you can also read around the topic, and please submit the feedback form if you have time to spare, and it would be good for you if you can submit your responses for the quiz as well. And I have uploaded the answers for the first quiz to the Moodle along with this lecture. Please go through that too. And if you have doubts after going through this lecture a couple of times and reading around the topic, please don't hesitate to contact me. So that's about it. Thank you.